Introduction to solids. What we have been looking for and studying over the last few weeks, months if you so choose, are basically two-dimensional figures. Once we get into a three-dimensional figure, that's when we end up getting the solids on it. Now, solids can have flat or curved surfaces. So, these are what you would normally associate with being a solid, right? Now, first one is called a polyhedron. You'd probably call it a box. Next one is a cone, which you'd still call a cone. Cylinder, can, or a pipe. Tube. Sphere would just simply be a ball. You know what these things are. Now, one of the things that we need to make sure that we're aware of here is the bits and pieces that we call things. Okay. So, if I wanted to classify the solid, figure has two parallel circular bases, lateral surface area. This is a solid cylinder. Now, the difference between a cylinder and a polygon is that the bases on a polygon will be polygons. They won't have a curve in them. Okay? Polygon kind of says it all there, doesn't it? Now, what about B? If you've seen that shape, that's more like a tent, isn't it? Okay. And the last one there being a cone. Kind of obvious, right? So, let's start off with this. So, let's go with, we'll try out with cold here. We'll start with you. So, what kind of a solid is that? So, Logan, what's its vertice? Okay. Does this thing have an edge, Gavin? Well, it wouldn't be X because that would just be the center of the circle that's on the base. Okay. But would the circle itself identify where the edge is? Yeah. So the edge of the circle or circumference of the circle would identify where the edge was. So that implies that its base is a what then? Circle. So, Keely, what about B? What kind of a solid is that? You're absolutely correct. It is not a solid. It cannot be. Okay. So, when we're looking at this, this is what we've seen with two-dimensional figures. Our three-dimensional figures are going to be drawn out in this fashion. So there's going to be a specific way that we see that they are identified. So, Jacob, how many vertices do I have here? Yeah. 4, yeah. Just MNOP. That's all it's going to be. So how many edges does it have, Caleb? Okay. And how many bases does it have, Parker? 4. That's 4 edges, 4 vertices. Well, first offhand, is it a three-dimensional figure? So is it possible for it to have a base? No. So as it goes through here, each flat surface of a polyhedron is called the face. Okay. The segment that is the intersection of the two faces is called the edge. So the edges are usually going to be identified as the lines that you see drawn out. Vertex is going to be where the edges meet. Now, a prism is formed by two parallel congruent polygon bases. Doesn't matter whether it's triangular prism where you get a triangle at each end. You've got something like this, which is a hexagonal prism because it has a hexagon top and bottom. Or if we're looking at this rectangular prism, rectangular solid, however you want to look at it, but it's got a rectangle on its base and its top. One of the words that you are going to run across with is called lateral. The lateral is just basically meaning the sides, what its sides are. Now, it's pretty easy to go through and figure out where the sides are, would be something on this or this. But on this one, because the base tends to be on the ends, the lateral goes the other direction. Could I take that three-dimensional triangular prism and just set it on its end to work with it if I needed to? Yeah, that would work just fine. So, pyramids. Pyramids are going to be identified by their base, polygonal base. So this is a square pyramid, this is a triangular pyramid, and I got 1, 2, 3, 4, 5, 6 sides there, so that's a hexagonal pyramid. Okay. Now the nice thing about this is it's pretty much straightforward. You've seen a lot of this stuff before. Not much new. We've got our edges, which is where the faces meet. We got that word lateral in here, so we know that that means sides. And as we continue on here, we see that there is also this possibility of having special names for things that have regular faces. Okay, a cube has square faces. Well, square faces are regular polygons. If I were to look at this one up here, this triangular pyramid, I could make it with, let's see, I'd need what, 4 equilateral triangles, and I'd be able to create that pyramid, correct? So, like I said, a lot of this stuff you are already aware of. So if I take a look at this one, this is a triangular pyramid, right? Triangular prism. You're pretty easy to go and take a look at it, identify what the bases are, and then determine what type of shape that it is going to, or solid that it's going to be. So, Hannah, what kind of polyhedron do I have there? Okay, but what kind of pyramid? A what? A hexagon, yes. So we got a hexagonal prism, or hexagonal pyramid, sorry. So is this a regular polyhedron, though, when it comes to looking at this, Aaliyah? Okay, but regular in this case does not mean normal. It has to have all sides the same. A cube would be a regular polyhedron. No. Would it even be possible to have a regular pyramid? No. So when I get to the next one, what type of polyhedron would that be, sir? Okay. Okay, it's got a pentagon as a base, but what type of solid is it going to be now? Yeah. So we got a pentagonal prism there. So is this one a regular polyhedron, Tessa? No. Again, granted, the base is the same and the sides are the same, but not all of the faces are the same. So, if I want to describe the characteristics of a solid, okay, let's see, assuming that all angles of each pentagon are congruent, is this regular polyhedron? Well, no. This would want to identify that all of these edges are the same. Okay. Let's see, so how many edges does it have? Well, I could count those out. 1, 2, 3, 4, 5. Well, there's 5 here, there's 5 there, right? And then there's 1, 2, 3, 4, 5 more connecting them. So I got 15. That's fairly easy. How many faces does it have? Well, there's 1, 2, 3, 4, 5 there with the lateral. And with the ends, there's 7, yeah. Now, when we are talking about a diagonal, we are talking about a line that goes from one vertex to another vertex through the interior of the solid. Now, one of the things that I definitely want you to have written down here is Euler's formula. We will be using that a little bit, so I'll give you a few moments to make sure that you have that down. All right, so we're going to continue on here with this, and using Euler's formula, how many faces does a polyhedron with 12 vertices and 18 edges have? Well, the formula is E minus F plus V is equal to 2, correct? Okay, so how many edges does this thing have? 18 minus faces, I have no idea, plus the vertices, which is 12, is supposed to be equal to 2. Yes. Well, when I asked you if I wrote it down correctly, you said yes. Oh, you raised your hand? Oh. So V minus E plus F. So you want V minus E plus F. Is that better? Good. So vertices, 12 minus E, which was 18, plus F. There we go. So if I go and take 12 minus 18, that would give me 6, plus F is equal to 2. That would be negative 6. So then we have to add 6 to both sides, add 6. So that means this thing has 8 faces. Okay. Comes in kind of handy if that's what you need. So, give you a moment and I want you to do this one. So who believes they have the correct answer? Yes, sir, what you got? 21. So, it's V minus E plus F is equal to 2, correct? So we've got 14 vertices. Let's see, and we have 9 faces minus E plus. So if I combine those two together, that gives me a grand total of what? 23? Let's see, so I got 23 minus E, sorry, write that out nicer. Minus E plus 23 is equal to 21. I'm getting ahead of myself, aren't I? I'm going to subtract 2, add E. That way things will go positive for me. So that looks like I end up with 21 is equal to E. Absolutely correct. Not a bad formula to deal with. So, let's take a look at this. Diamonds are cut to arrange them or to change them from a rough stone into a gemstone. Figure below shows 2 steps in cutting a particular diamond. If each of the other vertices is cut in the next step, what is the number of faces, vertices, and edges of the diamond in step 4? Okay, so let's go with our starting point. So if I want vertices, edges, and faces. So how much does the first one have? The original. How many vertices? Well, it looks like I got 1, 2, 3, 4. Looks like I have 4 vertices, right? How many edges? 1, 2, 3, 4, 5, 6 edges, right? Am I right so far? How many faces? 1, 2, 3, 4. So we got 4 faces. So after I do the first cutting, How many faces do I have now? Well, I've got 5, so that means that we added 1 to it, right? How many edges are there now? 9. Well, it looks like I added 3 edges, right? So now I'm at 9. And let's see, how many faces do I have? 5. So I added 1. So let's, now that we've got this pattern down here, I want to see if this actually works out for number 2. So my vertices now should be 6. Well, let's see if I count that out. I've got 1, 2, 3, 4, 5, 6, 7. Uh-oh, what went wrong? Yes. Okay, because after I made that first cut, there were 4 vertices. There's 1, 2, 3, 4. Now there's 1, 2, 3, 4, 5, 6. Oh, so it wasn't 5, it was 6. Okay, so we seen that there was an error there. So that's 6, and we add 2. Because when I counted, I definitely did not get 6 there. So if the rule is add 2, there should be 8 here, right? So let's count this out now. 1, 2, 3, 4, 5, 6, 7, 8. Hey, that worked out just right. So here the rule is adding 9, so that means I should have 12 edges now, correct? Let's see if that actually worked out. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, that worked out right. So I counted that out right. So now how many faces do I have? Well, I've got 1, 2, 3, 4, 5, and then the back one is going to be 6. So what's we said, add 1, and I get 6. So I found the rule so that if I cut the next one down, so if I do the third step, how many should be there? Well, that should be 10, right? Okay. So if I cut the next one down, I get 10, and then I should have 15, right? And there should be 7 faces. So when I do that fourth cut, that means this is going to be 12, 18, and 8. Okay. So it's really just once we identify what the pattern was and apply the pattern all the way through. So I'm going to give you a few moments, and I want you to go and do this one and then verify the results. So let's see how you did. So we're going to take a look at the original. So we've got vertices, we've got edges, and we've got faces. So when I take a look at the first one, my vertices are, well, let's see, there'd be 8 of them, correct? I get 8 vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges, and 6 faces. So after I go and take care of, let's see, they want the first 4 vertices. So we want 1, 2, 3, and 4. So if we would slide this one down, how many faces, or correction, how many vertices do I add when I do a cut? I add 2. I just don't want to take a look at this and say, well, how many do I have now at this point, and say 3, because we did take 1 away from the original was there, so we added 2 more, so we can go plus 2, so that means that there has to be 10. Edges. Now, how many edges were added on when I did this? Well, it would have to be 3. So now I am at 15. Because here, this edge, and this edge are still these 3 edges here. So 3 new ones were added. And so by grinding it down there, how many faces did I add? I added 1, so now I am at 7. So that means that this should be 12, 14, and 16, yes? That means this should be 18, 21, and 24. That means this should be 8, 9, and 10. Now, is this actually accurate? Did I get it right? So, the formula again is what? V minus E plus F? V minus E plus F is equal to 2, correct? So that means vertices was 16 minus the edges, which is 24, plus the faces, which is 10, should be equal to 2. Well, 16 minus 24, last I checked, was negative 8. Negative 8 plus 10 is 2. So it worked out. So there you go. Assignments due at the end of class tomorrow.